Okay, so here's the final video in the three-part for doing integrals from first principles, from Riemann sums. We have a shortcut that we're going to learn, or maybe you have learned from the fundamental theorem of calculus, but being able to do these by hand, just for one or two really simple examples, is really a good way to illustrate this. So the example we're going to do is a pretty easy example if you have the fundamental theorem of calculus, but we're going to do it from scratch. And we're going to use the two sums that we used in the first video. I'm sorry, in the previous two videos. So let's go down to it. I'm going to try to find the area under y equals x squared from 0 till 1. Here's 0, here's 1. So this is a really easy task with FTC. If you haven't seen that yet, don't worry about it. But having those sum identities from the previous two videos will really help us out. And it will also help you appreciate just how powerful the fundamental theorem of calculus is, because this is going to be quite a bit of work, and FTC allows us to skip all of it for every function. So we're going to do this with Riemann sums. Remember the idea behind Riemann sums. I'm going to answer the first question. Actually, we'll map out our game plan. We're going to do the Riemann sum for left. Actually, we'll do right. For right-handed rectangles with n rectangles. I haven't told you what n is, but the idea behind the integral is that we can evaluate that and then take the limit as n goes to infinity of that answer. Why? Because if I take the limit as n goes to infinity, n is the number of rectangles, and then I take that limit if I let there be infinitely many rectangles, quote unquote, or in other words, if I increase the size over and over and over, that offshoot, that extra, the overshooting or undershooting, should just go away. So the first part of the video, which is going to be basically all of it, is going to be the first task. And this is going to be just like the other example we did before. Except I haven't told you how many rectangles. I'm just unspecified n. So what do we do first? We always cut up the interval that we're finding the area under into n pieces. So it's hard to draw because I haven't specified. But I have n of them. And they touch the graph on the right. So I'm not drawing this one, I'm drawing an ellipses here to say there's more squished in here, but the idea still holds. So just because I've drawn, how many rectangles did I draw? 1, 2, 3, 4, 5, 6, 7. Just because I've drawn 7 and cut it up into 8 pieces, I haven't told you. So the width of each of these rectangles is 1 over n, because I've split up length 1 into n many pieces. Once I do that, this x value is 1 over n. This x value is 2 times 1 over n, because I have to go 1 over n twice. This x value, so that's 2 over n, is 3 over n, 4 over n, 5 over n. So, and then I skip a bunch, and then right before right before, so this is the nth one. So this is n over n. Or just 1. But the one right before, how many times do I have to go across on this interval? Well, n minus 1 times. And the one before that is n minus 2. So now I can just go ahead and do my base times height. The area is approximately, here's my base times my height. The height of each rectangle is just the function on the right side. It's just the y value. So it's the function at 1 over n, which is 1 over n all squared. Then I do base of the second times height of the second. And then I do base of the third times the height of the third. Sorry, not cubed, squared, because it's the function x squared. And then I do the base of the next one and the height of the next one, and hopefully you can see, I'm going to skip a bunch of them. I end with the base of, I'm going to do this rectangle. The base is n minus 1 over n. And then the last one has a base, this is the last rectangle, 1 over n times f of 1. So that's just 1. But I'll write that as n over n, and you'll see why in a second. So now I'll just simplify. 1 over n times 1 over n squared plus, well, 2 squared over n. Sorry. Well, I'm trying to do it one step at a time, but you can figure it out. I have 1 over n cubed here, because it's n squared and n squared and n are n cubed, and I've got 2 squared on top. And now I've got 3 squared. And now I've got, this should be squared, 4 squared, and I have n cubed. And I keep going. My second to last one is n minus 1 all squared. I've got n cubed on the bottom. And then I've got n squared over n cubed. So take a break for a second and let's figure out what we've just done. If you give me a number n, let's just say 100, and plug it into this formula, this is giving you the area under 100 many rectangles in this interval. So it looks really crazy because there's a lot of letters going and there's a lot of n's, but don't let that confuse you. And pause and rewind if you need to go back again. So now I'm going to find so now I'm just looking to simplify. I'm just going to simplify it. I'm going to bring everything on the same denominator because everything's got the same denominator. And I've got 1, 2 squared, 3 squared, 4 squared. Got all the numbers in between. I've got n minus 1 all squared and n squared. But this is exactly the what we did last time. This is the last video. We did this formula. This is the sum of the first n squared whole numbers. So that was, if you remember, n plus 1, 2n plus 1 over 6. And that's all over n cubed. And then I'll just put the 6 downstairs. n plus 1, 2n plus 1 over 6n cubed. I think that's all I can simplify it. So this is the Riemann sum for right-handed rectangles with n of them. If you give me 1,000 and you plug it into this formula, that'll give you the approximation that has 10,000. I can't even draw them that small. I mean, they'll go up and they'll go up and they'll go up and they'll go up, and There's 10,000 of them packed in that length 1 interval. The idea is the integral is just the limit of as I add more and more and more and more rectangles. So now I'm going to take the limit of this. How am I going to do that? Well, if I plug in infinity, I get an infinity over infinity situation. So I probably want to, at the very least, I don't know just yet, I'm going to expand all of this out. I'll distribute this one first. N squared plus n, 2n plus 1, 6n cubed. Sorry, I forgot the limit out here. And actually, I should have written it vertically, because I'm going to run out of space. And now I'm going to FOIL this. First is 2n cubed. Outer is n squared. Inner is 2n squared. Oops. Last is n. And that's over 6n cubed. So I actually can simplify this already. I can take an n out of everything. 2n squared plus n plus... Sorry, I can collect these first. I have like terms. N squared plus 2n squared is 3n squared. So when I factor a n out of that, I get 3n. And then when I factor an n out of here, I get 1. Sorry, I gotta factor an n out of the bottom too. Sorry, I made a mistake or two there, so make sure you're with me. Now I've got this limit. I'm going to split the fraction. So I'm going to take this separate. There are a couple ways to do this limit, but this is just one of them. 2n squared over 6n squared is just 2 over 6, which is a third. 3n over 6n squared, I'll actually just write that out. And then 1 over 6n squared. I see I can cancel this. 1/3 plus 3 and 6 are a half, so that's 1 over 2n, and then 1 over 6n squared. Now this looks like something I can take the limit of. As n goes to infinity, I have only n's in the denominator here. So n is a really, really, really large number. What is 1 over that really, really, really large number going to be? Well, it's going to be 0. So this limit is 0, this limit is 0, and I'm left with this solid 1/3. And that is the integral from 0 to 1 of x squared. That is the area under x squared from 0 to 1. Now you can probably appreciate, if you know the fundamental theorem of calculus. If you don't, that's okay. You can stop now. But if you do, the way that you know how to do this integral is to find an antiderivative and then plug in the bounds. You plug in 1, you plug in 0, and you get a third. That's how much work the fundamental theorem of calculus saves you. So that is, and also we had to spend 20 minutes of videos getting this. This was the whole point. This was the whole point of the last 2 videos. Took 2 videos to do this, and another 15-minute video to actually get the answer. So hopefully you can start to appreciate just how much work integrals are, where derivatives are much, much, much easier. So hope that was helpful, and take care.